Test. Test. Cool. Went to the post office and ate. It's time to read about monads. There's nothing so practical as a good theory. Finally, we come to one of the most talked about structures in Haskell, the monad. Monads are not strictly speaking necessary to Haskell. Although the current standard for Haskell does use monad for constructing and transforming IO actions, older implementations did not. Monads are powerful and fun, but they do not define Haskell. Rather, they're defined in terms of Haskell. Monads are applicative functors, but they have something special about them that either makes them different. That makes them different and more powerful from either app or fmap alone. In this chapter, we define monad, look at its operations and laws, look at several examples of monads in practice, write the monad instances for various types, and address some misinfo about monads. It's not a burrito. Okay. As we said above, a monad is an applicative functor with some unique features that make it a bit powerful than either alone. A functor maps a function over some structure, and applicative maps a function that is contained over some structure. And then appends the 2 bits of the structure. So that's one way to put it. So you can think of monads as just another way of applying functions over structure, with a couple of additional features. We'll get to those features in a moment. For now, let's check out the type class and its core opus. So given an applicative M, monad M. So bind monad A takes in a monad A and a function mapping A to a monad of B. This is a monad of B. Return. Takes A, puts it in a monad. We're going to export. Я это понимаю, брать. So we're gonna explore some. So this is like when you do return to like print something. When your function is in the IO monad. And your A. Yeah, that's kind of dope. Applicative M. Older versions of GHC did not have applicative as a superclass of monad. Given that monad is stronger than applicative, and applicative is stronger than functor, you can derive applicative and functor in terms of monad, just as you can derive functor in terms of applicative. You can derive applicative and functor from monad. You can derive functor from applicative. Okay. What does this mean? It means that you can write fmap using monadic operations. Fmap fxs is equal to xs bind return dot f. That's pretty dense. Well, let's look at it. Can I type? Am I not on the home row here, or what's going on? Q, GHCI. There we go. Fmap plus 1. Let's just do 1. It's the same thing. Oh, wait. Wait, I'm stupid. Plus 1. Maybe 1. Huh? Am I cooked? I'm gonna be cooked. Or just 1. It should be just 1. Just 2. Just 2. Bind. What is it? Bind. How do you do it? Oh, it knows what the bind operator is? Kind of dope. Return dot plus 1. Just 2. So what is it doing? It's getting 2. This is function composition, so that's the same as return of this. Wait, I don't understand that. It's a law, not a convenience. Dude, my neck is so clapped. Back. We'll explore the relationship between these classes more completely in just a bit. Functor depends on applicative, depends on monad. Core ops. 3 core ops, but you only need bind. Bind does that. That does that, and return does that. Return is pure. Okay. Sequencing operator. Sequences 2 actions while discarding any resulting value of the first action. The big bind. Bind is called bind. It contains things that are special about monad. Sometimes use it directly, other times indirectly via do syntax. The question we ask ourselves is, what's unique to monad, at least from the point of view of our types? It's not return. That's just pure from applicative. It's not sequencing operator, which has a counterpart in applicative. And it's not bind, at least not in its entirety. The type of bind is visibly similar to that of map, to that of fmap, and app, which makes sense since monads are applicative functors. For the sake of making this maximally similar, we're going to change the monad of M to F. So fmap takes a function and a in some structure and returns B in some structure. So it kind of goes into the structure, maps A to B, returns from within that structure. Applicative takes a function in a structure and a parameter in a structure and returns an output in a structure. Monad returns a value, takes a value in a structure and a function that converts values to values in structures and returns value in the structure. So it goes into the structure and just returns. So it seems like it's doing even less than applicative, kind of. Because this is going like in the structure and back out of it. This is going in the structure and you can just return straight out. If B is equal to FB, fmap functor, and 1x is equal to x1, and 110 is equal to 10, 1. Fmap and 1, 4, 5, 6. The type of that. Okay. So you want to discard one layer of the structure. Concat fmap and 1, 4, 5, 6. 4, 5, 6, in 1, flatten it up 1. So go out of this structure. Type of concat fully generalized. Concat the foldable T. TA. That's interesting. Map to A. Otherwise, you can just do a list of A mapping to A. It's a generic version of concatenation. So join on a monad M. M with a monad A in it. A monad with a monad A in it just goes up a level. And it's the inner level that's dissolved. Write bind in terms of fmap and join. Say less. So, do we have join and scope? First off. No. So let's find join. Join. So type monad M. M A Just trying to define it. Import control.monad join. There we go. So we gotta define bind. So bind monad A and B MA and B. So bind so we'll call this function F and MA. F equals MA, that's good. So we need to so fmap. So we need to do fmap MA. And then I'll apply this function in here, and then we have join. So we need to join this. So join F MA. Bind T bind. So how are we testing bind? What was the bind test here? What did bind do? So let's see if this works. 1, 3 bind return dot. Might need to do plus 1. I think it's gonna be bind. Here we go, return dot plus 1. So it doesn't look too correct. F equals MA join. Join a lifted episcope, you're applying MA. That look good to me, bruh. Alright, I mean, that was my solution. I'll see what it is in the answer eventually. Since monad is somewhat abstract and be quite slippery, many people talk about it from one or two perspectives they feel much fun. They address it from the IO monad. IO does have a monad instance. However, understanding monads through that instance leads to limited intuitions for what monads are, and a wrong notion of what IO is all about. Monad is not impure. Monadic functions are pure functions. IO is an abstract data type that allows for impure or effectful actions, and it has a monad instance. But there's nothing impure about monads. An embedded language for imperative programming. Simon Peyton Jones, one of the leaders and researchers of Haskell and its implementation at GHC, has famously said Haskell is the world's finest imperative programming language. And he was talking about the way monads handle effectful programming. While monads are often used for sequencing actions in a way that looks like imperative programming, there are commutative monads that do not order actions. We'll see one a few chapters down the line when we talk about reader. A value. The type class describes a specific relationship between elements in the domain and a domain and defines some operations over them. We refer to something as a monad. We're using that the same way we talk about a monoid or a functor. None of these are values. Not strictness. Monadic operations of bind and return are non-strict. Some operations can be made strict within a specific instance. Talk more later. It doesn't require knowing math or category theory. It does not require mystical trips to the tops of mountains or starving oneself in a desert. It is a generalized structure. The monad type class is a generalized structure manipulation with some laws to make it sensible, just like functor and applicative. We sort of hate to diminish the mystique, but that's really all there is to it. Free love. The monad class also includes a set of lift functions that are the same ones that we already saw in applicative. They don't really do anything different, but they are still around because some libraries used them before applicatives were discovered, so the lift m set of functions still exists to maintain compatibility. So you may still see them sometimes. We'll take a short tour of them, comparing them directly to their applicative counterparts. So yeah, applicative lift, AB, onto A. It's not just fmap. Am I tripping? Yeah, okay. Just have the upper dimensional variance. Zipwith is lift, specialized to lists. Depends on which list monoid is being used. Alright, then we have the threes. That's just the same thing, but three-dimensional. Do syntax and monads. We introduced do syntax in the modules chapter. We're using it within the context of I/O as syntactic sugar that allows us to easily sequence actions by feeding the result of one action as an input value to the next. While do syntax works with any monad, not just I/O, it is most commonly seen when performing I/O actions. This section is going to talk about why do is just sugar, and demonstrate what the join of monad can do for us. We will be using the I/O monad to demonstrate here, but later on we'll see some examples of do syntax without I/O. To begin, let's look at some correspondences. Star right, next an applicative, Function, a function returns a function. Double star, right? Sequencing. App sequence, M sequence. Wish these had names. Still runs the function. Yeah, you need to join them. Join. Join. Put stir. Line. Fmap. Line. A. A. SDFJ, okay. Okay, check. Let's go with coders crave. Name, please. Name, get line. Why, hello there. Dude, this guy's gotta stop being so freaky with his variable names and examples for name, please. Yeah, it's pretty aged to read. Take a list of A. Mapping A's to B's. A's to list B's. Or what's to B? Whatever. Take a maybe A. You got an A function that maps A's to maybe B's. Turn a maybe B. Cow. Cow's got a name, an age, and a weight. Deriving EQ and show. No empty. Takes a string and returns maybe a string. If it's empty, return nothing. If it's not empty, return just a string. Seems legit. No negative. Takes an int, returns maybe an int. So you get some guards here. Non-negative n. If n is greater than or equal to 0, just n, otherwise nothing. Cow's name is Bess. Must be under 500. So weight check. Cow, maybe cow. You got a weight check. C. So what are we doing with C? You got the weight in the name. If name is Bess and weights 500 or more, then nothing. Otherwise, just C. Make spherical cow. Okay. Take a string in it and an int and maybe a cow. Make spherical cow name prime, age prime, weight prime. Case no empty name prime. Nothing nammy. Mamie. Case no negative age prime of nothing, just agey. Case no negative weight prime of just weighty. So if they all pass the not negative thing, then just weighty is equal to weight check, cow name 80 weighty. Weight check returns just the cow, or okay. So make sure cow best 5,499, just cow best, otherwise nothing. Okay, so let's clean it up with the monad. So we can't do this with applicative. Name prime, H prime, weight prime, do naming, no negative, no empty name. AG, no negative age, weighty. It's kind of gated. Wait, this is really hard to visualize. Uh, hmm. Yeah, that's really hard to like map in your brain. Hmm. Maybe A. It takes a maybe A and a function mapping A's to maybe B's and returns. Ah, okay. So it's when you want to chain a bunch of them that operate on A and return a maybe A, but you want to chain a bunch of them together. So you want to go in the maybe and then flatten all the maybes with bot. Okay. Understanding. So this is like you want to pipe effectively. So you have all these functions that validate the cow. You're seeing if it's empty name. Okay, then do that and it's empty non-negative. Then do this and it's weight's non-negative. Then do this and let's check the weight. But if you just did this every time, you'd just be stacking a ton of maybes on top of each other. So you need to use monad to say here it's nothing. It's nothing, then do nothing. You also want these to take a string, not some amount of maybes wrapped around a string. Okay, that makes sense. So this takes the name, it's a string. Alright, this would be a maybe string. And we have this, we take the age, and that's a maybe age. This returns a maybe, but we just want to turn one maybe so it joins here. So this is the only one that actually matters, right? Yeah. Oh, fall asleep, dude. No time to be tired, yeah? Rick, dude, I just need to take a nap. So either E or A. Take an A and map it to an either E, B. So this is like for area. EP. Type founded int. Type coders int. Data software shop is a founded in coders. Programmers. Negative years founded. Too many years founded. Negative coders, too many coders for years. Got a bunch of validation functions. Make it's gonna be either a founded error or a software shop. Years coders do founded years. Programmers div founded. AP is just a rename. Monad laws. Need a little reset here. Hit a glasses wipe. we're using checkers. I think that makes sense. If you invalidate the rules, your thing will not exist. Composition under functors just works, huh? Dude, why did I just get like so tired for a second? Like falling asleep level tired. It's around 12. How long was I like snoozed for? Oh my god, got 2 minutes. Just took a casual 2 minute nap. You know how it is. You know how it is. That is not 1440p. What am I itching my forehead like that for, bro? What am I doing, bro? Kid is dumb, bro. Alright. The situation seems less neat at first. Let's attempt to define composition for magnetic functions in a simple way. mcomp. Yeah, this is kind of aids. I don't know if I care to do all that. Chapter exercises. I'll read the definitions, but I'm not doing those. Monad is a type class reifying an abstraction that is commonly used in Haskell. Instead of an ordinary function, type A to B, you're functorially applying a function which produces more structure itself and using join to reduce the nested structure that results. Yep. A monadic function is one which generates more structure after having been lifted over a monadic structure. Seriously. Looks finish. Looks very finished there. And maybe not the EI as much. Swiss. Maybe. Bind is a bit overloaded. Binding variables to values, yeah. Mobits. Not about ordering or sequencing. It is roasting the binary package. Do? What does M do? What the heck is M do? Dude, if your blog looks like this, you're probably good. If your blog is a mailing list, you're probably good. Okay. Well, I kind of feel bad for this dude. He got freaking roasted for his use of the put monad. Bro got freaking wrecked. Oh, maybe I should read this. Applied structure. Less than 30 pages. All right, we're going to read applying structure. Some cringe quote about repeating. Okay, this is actually really useful. This is like, when do you use these? Templating content in Scotty. So the Scotty Web Framework's Hello World example uses mconcat to inject the parameter word into the HTML page returned. Scotty 3000 do get word do beam param word param in the word. So this is like, I guess we're just looking at this. So we have some HTML work. Mconcating Scotty beam param word. Oh, so this is like the ID of the URL. Getting this. So this is like getting the map. Okay. We're calling that beam. This is why you don't use random. Is Scotty Beam like a person or something? Dude, don't use random names. Just make stuff make sense, bro. So this is your slug here, slug, parent, into beam. Then we have HTML. It's calling HTML with this. So we're concatening. So we're concatening these. Scotty, beam, hit me up. This is monoid. Yeah, I mean, that makes sense. Concatenating connection parameters. It's from. Wait, how do you pronounce this name properly? Why is this a minimal?
The following pronunciation is brought to you by
Aditya. Aditya.
Okay, from Aditya Bhargava. Making a website with Haskell. Use Scotty. Using foldar and monoid to concatenate connection parameters for connection to the database. That's kind of cool. I mean, that's just so much. Just another way we should do plus, but okay. Run DB, SQL persist, resource TIO, IOA. So is this a foldable? I don't know enough to say what this is. Run DB query, do. So DB connection params. That's something. We're calling it and getting params out of it. Then we're folding connection string. We got key values from T. T. This is append, yeah. Append. Or I guess it's concat. Encode UTF-8. The key equals the value space. Oh, Xmonad, well. Windowing system for X11 written in Haskell. Configuration language is Haskell. Using monadic, or is this? I guess this is just it's not monadic append. This is monoidic append. So you're binding keys to stuff. Keys equals C from list. This is just not. Like, I enjoy learning about this, but like, am I gonna use, like, why would I do this? It's not like particularly fast or maintainable. Just like, Piece is a function. The monoid of functions. Point data monoid, consum 1, consum 2. F9001. Get some 1. Dude, I just want to get to parser combinators, bro. I'm skipping the rest of that. Articulated parsers, let's go. So he's got an info option, rev state TH-JSON format. No idea what that is, but well, you can imagine this is like the long, like the dash dash JSON dash cap J help. Okay. Parser info helper verse switch. So you can imagine this is being applied like here, right? Or here, I guess. It's kind of hard to see. But this is sequencing. Okay, so you're doing something with effects, you want to discard value that results. Lift data constructor for the payload type over the parser. JSON object, basic annotation text seeds furthermore, JSON values from strings. Parse JSON takes a value, turns a parser A dot colon from JSON object text into a parser. Okay. Instance from JSON payload. So is he making payload? So is someone from JSON for payload. Parse JSON. Object V payload. Okay, I mean, I have no idea what's going on right there. Takes a function map and A to bool, and a function map and A to bool, and it goes A to bool. Lift A2 or. True or false? It's like a double or. So it's like if this is true for either. Interesting. So yeah, let's get back to it. We've decided about polymorphic literals. Yeah, I don't really care. I don't care about this. I'm not trying to be too pragmatic with it. It's a wrap. Oh, okay. It's kind of free. Foldable. That's just 14 pages. What's the big one here? Parser combinators is huge. Or that's composing. Yeah, parser combinators is what I'm trying to get to. Foldable is so short. Alright, we're reading foldable. We are reading foldable. So let's update this. Haskell monad. Structure. Foldable. Traversable. I'll do this as well. So we're gonna do foldable and traversable. Then I'll do another stream. I'll probably play again a game of Counter-Strike. Do another stream working on Gleam dependency resolution. E. Yeah, that's it. Alright. Foldable. This type class has been appearing in type signature since at least chapter 3, but for your purposes in the third chapter, so that you can think of a foldable thing as a list. So yeah, what's foldable besides a list? I wish I could talk faster. A list fold is a way to reduce value inside of list from one summary from some function. The folding function is always dependent on some mono instance. That makes sense? The folds we previously wrote mostly relied on implicit monoidal operations, but you can have some more generalized catamorphisms to other data types depending on the understanding of monoids for the structures and in some case making them explain. The foldable class and its core ops, the monoidal nature of folding, and standard operations derived from folding. The foldable class. The package documentation for the foldable type class describes it as being a class of data structures that can be folded to a summary value. Agreed. The folding operations that we've seen previously fit neatly into that definition, but this type class includes many operations. We're going to go through the full definition a little at a time. The definition in the type class in the library, the definition in the library begins. Class foldable T where minimal fold map folder. Ladma. The minimal annotation on the type class tells you that a minimally complete definition of the type class, indeed, will define fold map or fold R for a data type. As it happens, fold map and fold R can each be implemented in terms of the other. Oh, okay. And so you can do either one. And the other operations included in the type class can be implemented in terms of either of them. Interesting. As long as at least one is defined, you have a working instance of foldable. Some methods in the type class have default implementations that can be overridden when needed. This is in case there's a more efficient way to do something that's specific to your data type. If you query the info about the type class in GHCI, the first line of the definition includes the kind signature for T. So, class foldable T, it's a higher kinded type. And it's two of them. That T should be a higher kind of type is not surprising. Lists are higher kind of types. Indeed. We need T to be a type constructor for the same reasons we did for functor, and you'll see that the effects are very similar. Types that take more than one type argument, such as tuples and either, will necessarily have their first type argument included as part of their structure. You need GHC 710. Well, the prelude, foldable type class, not all foldables in the prelude. Data foldable, data monoid. Revenge of the monoids. One thing that we did not talk about when we covered folds previously is the importance of monoids. Folding necessarily implies a binary associative operation that has an identity value. True. The first two operations of find and fold will make this explicit. Class foldable T higher is 2 parameter. Or I guess it's a 1 parameter kind here. I'm not exactly sure how to read that properly. I kind of don't fully understand it's type to type. So I think you need a type. I think that means it needs one type, whereas if it was just star, it would just be the type, yeah. Okay. So yeah, a list needs one type. Yeah, so that's type to type. Class foldable T is type to type, where fold, data monoid M, TM to M. So that's not really sure how that works. You have this monoid. You have this type. Oh, so you want this monoid to be in that type. So it's like a list of something that's a monoid. So you can imagine a int, if you just want to class it down to like the sum type, the num sum monoid, you can have a list of some monoids, do something over them, perhaps sum them up, and have this other get sum at the very end, yeah. And then fold map. So you have the same monoid. You can imagine this is sum. We have a function mapping A to M and a list of A and M. Okay, so this is like, yeah, fold map. That makes sense. So this is like, imagine having a list of sums. Sorry, imagine having a list of nums. Imagine having a list of numbers. List of ints. And a function mapping ints to sums. Or you could even just look at this as maybe. Imagine the monoid is maybe a monoid. Yeah. Imagine the monoid is maybe. You're mapping through the monoid. It kind of works better. It's not, yeah. That doesn't suffice. That doesn't work with the T as well, though. I don't think. I don't know. It is a lot easier to think of it as a list. So fold map. Imagine you have a list of ints and you want to produce their sum as a get sum type in the sum monoid. So you have the sum monoid. You have a function mapping ints to sums. Then you have a list of ints and you produce a sum. Yeah, okay, that's makes more sense. So fold allows you to combine elements inside a foldable structure using the monoid defined for those elements. Fold map first maps each element of the structure to a monoid and then combines the results of these in that instance in the monoid. This might seem a little weird until you realize that foldable is requiring that you make the implicit monoid visible in the folding operations. Let's look at a very basic foldr implementation and see how it works. Foldr plus 0, 1, 5, 15. So plus is the monoid. 0 is the initial. We have a list. So I'm not sure what the signature for foldr is, but I think this is like the initial value, yeah. Binary associated operation for that fold is plus. We've done it without thinking of it as a monoid. Numbers in our list have other possible monoids. Is not relevant. Yeah, so this is kind of... So maybe it's not as much about sum, it's about actually being more explicit about the monoids, perhaps. I was thinking more of the sum. Well, yeah, if you do import, what is it, data.monoid, you do tsum. Sum is a function mapping A, so like sum to get sum to sum. So sum, the type, sum A. Yeah, it is. It does implement monad functor applicative. I don't think the there's no point right here. Specified over that being monoid. We can already see from the type of fold that it's not going to work on the same type as foldr. It's not going to work the same because it doesn't take a function. Yeah, that's true. But we also can't just jump. We can't just fold up a list of numbers because the fold function doesn't have a monoid specified. Error message resulting from incorrect number of arguments. Error message. That is a monoid. So what we need to do is to make fold work is specify a monoid instance. Okay, so that was comparing fold R to fold. That makes sense. So what we need to do to make fold work is specify a monoid instance. So these must be instances of a monoid. So some, yeah, this is what I was talking about. Fold, you get the sum, you get sum. Or let's tediously fold some integer, yeah. Oh, okay, that's cool. Prelude, fold, product, and integer product. In some cases, the compiler can identify and use a standard mono for a type without us being explicit. So the standard mono, it's the string concat, fold R, doom. We're just adding them hello Julie, fold R. This is implied, and hello Julie. Default mono instances for always gives us neither the height specified. Now for something different. Let's turn attention to fold map. Unlike fold map has a function as the first element. Unlike fold map, the first argument of the function must fixing map each element of the structure to a mono. So we're mapping each element of the structure to its own monoid, it appears. So fold map sum. So now we're explicitly that's better. That's way better in my opinion. Fold map sum 1, 2, 3, 4. Fold map product 1, 2, 3, 4. Fold map all 1, 2, 3, 4. So this is like and yeah. Fold map any. So it's like or false, true, true. Fold map first, just 1, nothing, just 5. First, just 1. Fold map last, just 1, nothing, just 5, just 5. And it's get last. Okay. For example, is a function being implied as a data constructor. This data constructor identifies a monoid instance, the append for this types. It already contains enough information to allow fold map to reduce the collection of values to one summary value. Yeah, it does. Because it takes a append takes a little append takes a list, converts it to 1. So it chooses 1 out of a list. Ah, I've leached now. Yeah, that makes sense. So from fold map can also have a function map that is different from the monoid it's using. So here we have a function that's times 5, so there's a monoid here, and we're using a different function. Times 5 for the sum integer. Sum gets sum. 5. So it's summing them. Get sum 30. I mean, it's going to be curious which one is doing first. 5 times 1 times 3. 6, 30 versus 25. Okay, so it sums them first. So it appends this first, then f maps it. Yeah, so it does map first. Wait, does it fold first or does it map first? It folds this based on the monoid. Then it maps this. But if you fold this based on the monoid, into what monoid is it mapping? Or into what structure is it mapping better? What you're trying to fold only contains one value. Minimal foldable instance must have either fold R or fold map, and either function the type class must be derived from one of these. Let's look at some laws, right? We're now implement for identity. Let's kick things off writing foldable for identity. Identity A equals identity A. Fold R or fold map, or write both, just to know. Plus fold L, okay. Foldable identity, where fold R, FZ identity X is equal to FZX. Fold L, FZ identity X is equal to FZX. FXZ, sorry. FZX equal to FXZ. FZX. Swapping, so fold R's, keep swapping them. This would be done. ZX, FZ. FZX. Fold map F, identity X equal to FX. With fold R and fold R distance, I think it was already swapped. I didn't need to do anything special for fold map. I need to make use of the monoid for identity. Supply the function. Strange to think of folding one value. When we talked about countermorphism previously, we focused on how they can reduce a bunch of values down to one summary. In case of the identity countermorphism, then the point is less to reduce the values inside the structure one value and more to consume or use the value. Yeah, okay. That's true. Fold R times 1. Identity 5. Identity of 5 is 5, so times 1, 5. Fold L times 5. Identity 5. Apply the monoid, so you get 5 times 5, 25. fold map times 5 identity 100. Identity of this 100 times 5 500. Note that using fold map still relies on the mono instance for the a value. Yeah, it's just that the mono instance for this just returns a. Maybe. It's a little more interesting because unlike identity, we have to account for the nothing cases. When the maybe value that we're folding is nothing, we need to be sure we can return some zero value while doing nothing while the folding function, but also disposing of the maybe structure. Fold R and fold out, the zero value start value provided. Fold R plus 1, nothing, nothing. Oh, 1. Okay, so this is the minty here. Does it just generalize that to minty, or do you have to explicitly say that? On the other hand, for fold map, we use a mono with identity value as a 0. Fold map plus 1, nothing. For fold R, the 0 value, oh yeah, the 0 value is the start value provided. 1 plus nothing is 1. Fold map, we use a mono to identify as 0. Fold map plus 1, nothing. 1 plus nothing is just 0. Yeah, okay. When the value is a just value, though, we need to apply the folding function to the value and again dispose of the structure. So fold R plus 1. So we're going into here and doing plus 1 to 4. Fold map here, just 3. So just 3 is a sum. So 3 is the sum. Just sum 3. Okay, and then we do plus 1. So we're going into the just, into the sum. We're adding 1, so just. But the fold actually takes it up a level. So it's not just sum, it's just, it is sum. So it's fake maybe type again to avoid conflict. It's instance fold optional where fold R underscore Z, nada is equal to Z, fold R F Z, yep is equal to X. Sorry, yep X, fold equals Z, fold L underscore Z, nada Z, fold L F Z X, F Z X, fold map Z, nada, F F yep. Gotta assert a type for the monoid. Basic derived operations. Two S T A is equal to A. Pseudo S to A. 2S just 1 is equal to S to 1. 2S just 1. So we're mapping this list and we're replacing these monoids with the OS monoid. Concat map 2S just 1. So concat is kind of like join. Like join 2S 1. They're traversable as well. What's traversable? Lists, cons lists, trees. Curious how that works because they're like recursively defined types. Traversable allows you to transform elements inside the structure like a functor, producing applicative events along the way, and if these potentially apply to the applicative structure outside of the traversable structure. It's commonly described as a way to traverse a data structure, mapping a function inside a structure while accumulating the applicative context along the way. This is easiest to see perhaps through a demonstration example, so let's get them through it. Alright, I'm gonna shut up and eat my almonds. They're getting way too expensive, by the way. They're defined in terms of each other. The heck? What the heck? I don't understand that at all. Some. Add them. Fmap some. What the heck does this do? Sequence A, just one, just two, just three. Maybe it's just ignores some other things. Traverse. Flip bind. The frick is that? This is foldable, yeah. I've seen map M. Excuse me. I don't think he plays chess. So it's an IO action of either an error or some object. IO on the object. Pipeline function query do. Fetch the query, that's called A. K sequence map. So decode the function A. So we're decoding all these things in, we're decoding all these queries. And then, or I guess the query could be in a type, so it can be just one. I'm not sure what query is. Query is query. Decoding fetch function, it's IO string, okay. So it's a list of strings. So we're mapping in here sequence of left, so it's going to be either an error, return left, which is the error, or right response do. Make I on the object res A, return right A. That'll print it because it's IO. Monadically over the either, only to perform another monadic IO action inside of it. The 5 I'm gonna pare it down to. Dang. Query do a fetch function query traverse make I on the object map and decode function A. Make it point free if we want to. So this is de-doing. Traverse make I on the object compose map in reverse bind. What bind? Since map in is just traverse with a slightly different type. Traverse make I on the option dot traverse. I needed this one a little bit ago. Byte string easy. URL string over URLs. Mapping get. Response byte string map get URLs. That's the definition of get. Okay, so traversable takes the IO action out of the list. That's kind of smart. I trust I don't really care too much there. Traversable instances either. Tuple. So curious about the laws. Naturality. So T dot traverse F. How long is a reader? So if I do reader, state, and parser combinators, another day. And yeah. So that was the reading I wanted to do today. Haskell monad structure, foldable, traversable, and yeah, I'll be back on in a minute. Gonna play some Counter-Strike, look at my schedule. I think they just dropped a canvas and do some probably do nothing else.